Testing. That better? Okay. Check audio. Check. Okay, that's good. Unmute it and then we can talk in there and everything's cool. You just give it to them. There. Testing. And then here.
How's that work? Good? Okay.
Okay, so we're very pleased to have Abdelmalek Abdesselam from University of Virginia, and he's going to tell us about p-Adic quantum field theory, which I've hardly ever heard of.
All right, thanks, Tom, for the invitation. So that's the title, and just mention briefly. So this is joint work with my student Ajay Chandra and Gianluca, my colleague Gianluca Guadagni. They're both at UVA also. And this is part of a project which is funded by the NSF in probability theory. Okay, anybody here from automorphic forms, or is there serious arithmetic people here? No? Mostly math physics?
So you can remind us or tell us about p-Adic.
Yeah, I was wondering if you guys got the memo. The physicists were supposed to or to learn a little bit, review what the p-Adic number is, and mathematicians, if there was any, to learn what a Vick's theorem and things like that. All right. So I'll briefly explain where the problem comes from, and actually I'll try to delay the introduction of p-Adics as much as possible. So in the 70s, one of the big achievements of constructive field theory was the construction, for instance, of so-called phi-4 theory in 3 dimensions. So what does that mean? One way to see it is as constructing a measure on the space of distributions on R3, which looks like this. So integral, well, the measure is product over x in R3, d phi of x, and here exponential minus integral gradient phi squared plus m squared phi squared plus lambda phi 4. Whatever that means. Okay. So here phi is a random distribution. This is supposed to be the Lebesgue measure on S prime, and this is a Radon-Nikodym weight, which perturbs this Lebesgue measure by an integral over space of something local, gradient of phi squared, m phi squared, and phi 4. So it looks daunting like this, but it was done precisely. What people constructed in the 70s, more precisely, is called massive phi 4 3. That means that if you look at the value of your field at some point and at some other point, then the correlation decays exponentially or very fast as you take these points far apart. But a more difficult theory that still hasn't been constructed rigorously is the so-called massless case, or critical. And that's still unknown, and that corresponds to the situation where the correlations decay as a power law instead of exponentially.
Yeah, but we do know that there is such a theory.
Yeah, I think Glimm and Jaffe, proved that there.
You can make it critical too. I mean, so you know there's a phase transition.
Yeah.
Say in 3 dimensions, and then by correlation inequality, you know that there's a.
You know it exists.
You know it exists.
Okay.
You can't compute it, of course.
Yeah.
That's too hard. But
Yeah.
You know it exists.
There's no mass gap.
Yeah.
Okay.
So did the phi 4 3-dimension massive?
Massive, that was Glimm and Jaffe, then Feldman, Osterwalder, and Mania Senior.
You need the renormalization group or not?
Kind of, yeah. I mean, they did it with a phase, so-called phase space expansion, and no.
So there's renormalization.
Yeah, you need renormalization, but I mean, that was actually some of the ideas are you find them in both, but it was actually at the same time as Wilson was developing. And the first paper by Glimm and Jaffe was a contemporary. Anyway, okay, so that's understanding the long range.
What's the problem with this?
That's not important. I'll continue.
Because I'm saying that there's no
I'm not going to talk about this, so it's just
There's no problem,
motivation.
But there's no problem there, right?
Hmm?
The mass in the 543.
Yeah, that's been done.
Because you put the mass in the Lagrange. So there's nothing.
Yeah, okay. This is just motivation. I'm not going to talk about this. So, okay, so this is hard to analyze. I mean, the critical massless theory or the long-range behavior of correlations when you have this power law decay is harder to analyze, partly because it's supposed to be the same as Ising 3D. I mean, it's a very difficult thing. So what Wilson introduced was this Epsilon expansion, where you basically pretend that you're not in 3D, but you're in actually 4 dimensions minus epsilon, and try to do an expansion in this epsilon, and then put epsilon equal 1, and that's supposed to tell you things about this. Okay, so the problem is that we can't really do this non-perturbatively, so the best substitute for that is to play around with this, this thing here. So here we have basically phi minus Laplacian phi L2 scalar product. Instead of taking the Laplacian, you can play with the fractional power of the Laplacian. For instance, you can put here 3 plus epsilon over 4, where epsilon is small. Yes, over 4, yeah. And if you do this, then you're kind of mimicking what Wilson did with this 4 minus epsilon expansion. And for this situation, this model has been analyzed rigorously by Brydges-Mitter-Scoppola.
Excuse me, I don't understand. Epsilon small or epsilon close to 1?
Small. Epsilon small. It's like the 4 minus epsilon. You would like to take epsilon equal 1, but you can't. It's too hard.
Ah, okay.
So what they did is, for epsilon small, like you said, they constructed a so-called infrared fixed point for the RG. So I'll explain what that means. I worked on this model also, and I constructed what is called a trajectory, an RG trajectory going from the Gaussian ultraviolet fixed point to this infrared fixed point. But in order to go and get final results on this type of models, I thought that it would be nice to study actually a much simpler model than that. And that's the idea of the p-Adic. So basically, even this is a bit too hard. So, so what I'm going to talk about is a modification, which amounts to saying, well, instead of working over R, I'm going to work over the field of p-Adic numbers QP.
Before you go ahead, the Brydges-Mitter-Scoppola paper, there is also the ultraviolet. Both
No.
No.
They construct the infrared fixed point, and they construct the stable manifold of the infrared fixed point near the infrared fixed point.
The ultraviolet.
I did the trajectory which goes from the ultraviolet to the infrared. But I mean,
It's not ultraviolet.
huh?
Okay, so you did the
There is the UV fixed point. There is the infrared fixed point.
the Brydges-Mitter-Scoppola.
What they did was analyze this small region. They showed that it exists, and they constructed the stable manifold of this guy. But the stable manifold, as they constructed, doesn't go all the way here. What I did is to show that you can construct trajectories which go from here to here. In other words, that the unstable manifold of this guy intersects the stable manifold of this one.
Okay, but in the Brydges-Mitter-Scoppola, then there is an ultraviolet cutoff.
There is always an ultraviolet cutoff if you're doing RG.
No, okay. But not removed.
Not removed, no.
You removed it.
In a way, yeah.
Okay.
Okay, so that's the goal. But actually, what I'm interested in is really building a theory. It's not really solving a model or. So what I'm interested in is to develop a rigorous theory of what quantum field theory is, and also what the renormalization group is. You might not agree, but the way I see what a quantum field theory, at least in the so-called Euclidean picture, for me, is, as I said, is just a measure on S prime, the space of distributions. plus some extra stuff.
You want some properties, otherwise you haven't got it.
Yeah, haven't finished. So not just any measure. Yeah, you want some properties, but I don't care really about the properties in the literature. What I want, to restrict the problem a little bit, I want these measures to be constructed out of a Gaussian measure plus a Radon-Nikodym. I don't know how you write Nikodym. Like this. Modification, which is like the one I wrote here. So it would be exponential minus something integrated, which involves only local expressions. So exponential minus something local, integrated over space. OK. So typically, the Gaussian that people take is associated. It's the covariance of that Gaussian is associated to an elliptic. Is the Green's function for an elliptic operator minus Laplacian plus m squared, for instance. I think, I mean, from looking at what happens in other spaces like QP, really the important thing is you want to perturb a Gaussian, which is given by a homogeneous distribution. I mean, really, you want to perturb around the massless free field. And one of the problems is that these homogeneous distributions over R are more complicated than over QP. You will see that. OK. And of course, the extra structure. So what I would really want to get a hold on is that not only the measure show that the moments, which are distributions, are singular only on the diagonal when the arguments are the same. And I want, after that, to take some point to approach the diagonal, see what happens, get the operator product expansion, which should show that there is other fields that you need to construct. And even further than that, if we succeed, so this basically is constructing the so-called vertex operator algebra structure. If we can go even further, to develop perturbation theory around non-Gaussian fixed points. But that's way far ahead. Oops. OK. So maybe just to recall the general idea. So you have a space X, which you can think of as RD or soon as QPD. What do you want to do? Well, you want to introduce some lattices. So Lj is a decomposition or partition into boxes. And you want the size of this box to be of size L to the j. L is some fixed number, say 2 or 100, whatever. And j belongs to z. OK, so for instance, if I draw here my space X, well, you can cut it like that. But then you can cut it with finer boxes. So I won't draw them all. But for instance, this would be for size 1, size L inverse if L is equal to 2. You have all these hierarchy of lattices. OK. So the goal here is to put some random variables on the small boxes. So you look at the finest lattice in your system with mesh L to the R, and R is very negative. And you have at this. I mean, I'm not going to draw it on the same picture, but you can think of it as superimposed on top of it. Here you have the lattice with boxes of size 1. And you can also put everything into a big volume lambda, which is itself, you can take, for instance, a box of size L to very large positive number. So what's the idea? The idea is you want to so you want to put some random variables at each site here with a joint distribution given by a discrete version of this. Okay, so instead of Laplacian, take lattice Laplacian. Replace integrals by Riemann sums. And to have something which is meaningful, you have to confine your integral to this big box. Then we're going to remove the box. If you do this, you have a well-defined probability measure at the level of these little guys. And when you're doing an ultraviolet limit, you're trying to construct a measure like this on S prime. What you want is that if you say, look at the average, you take a unit box and you look at the average of what these little guys in the unit box are doing, and say you take also another box if you want. You look at the average of the little guys here. Well, you want these random variables, these coarse-grained random variables, to be well defined in the limit where you take the small lattice, go to 0. That's the idea. And typically what you have to do is that the parameters that you put here in your microscopic description of the joint probability distribution of your small variables, you have to allow these guys to depend on the lattice on the size of the small lattice. That's typically what you need to do. So, question: how to adjust these parameters for the small lattice as you take r goes to -infinity, so that the averages here give you well-defined random variables. Actually, you want the joint distribution of these random variables to be well-defined, but you want more, of course. You don't want stupid things like this guy completely independent from that guy, which would happen if you, so if you do, then you would construct a measure, okay, but you constructed white noise. It's not interesting. Other things which are not interesting are joint distributions which are Gaussian. That's also not interesting. Okay, so what you really want is to construct non-Gaussian probability measures on the space of distribution. And that's very hard. And even harder, non-Gaussian, so non-trivial, but also massless. That's even harder, which means that, OK, you have non-Gaussian distribution between these guys, but then if you take these unit boxes very far apart, they don't become, the correlation doesn't decay exponentially, but as a power law.
You might comment that, I would say this is true, and in fact, to some extent it's been proved, that in high dimension, you can't do this. So
yeah,
in
yeah.
4 or 5 dimensions.
Yeah, exactly. So in more than 4, it's proven rigorously that no matter how you adjust this guy and this guy as a function of the size of the mesh of the small lattice, there's no way you can succeed.
You get anything but Gaussian. No.
Yeah, you just get Gaussian.
No, because this is the lattice.
Yeah.
So above, you're right. Above.
Yeah.
Above 4, there's nothing.
No. So that's been proved by.
You think you're doing something by putting in that 5/4.
No. Excuse me, Doc.
Yeah.
So this is ultraviolet problem. So
Yeah. I'm talking about ultraviolet. Yeah.
So above 4.
But then you can ask, once you have constructed the measure, then you can ask yourself, OK, I have a measure. Is it critical? So you can just look at the correlation. Do they decay exponentially? Or
You can't, even in a box, you can't take the ultraviolet limits that you think.
yeah.
You're going to get nothing.
What I'm interested in is actually cases where you handle both problems,
infrared
the
and
ultraviolet plus infrared problem.
Yeah.
That's,
Both trivial.
yeah.
And the idea is if you take 2 Brownian paths, they're not going to cross, right? So
OK.
high dimension. That's one way to think.
Sorry, you had a question.
What scaling does the ultraviolet limit correspond to?
Sorry?
What is the scaling for what you call the ultraviolet limit?
Oh, ultraviolet is just a word for high momentum or high frequency, so that means short distance.
Yes, but is there
So-
scaling with respect to your integral here?
Yeah, so he has to adjust those parameters. So you want the ultraviolet limit means he wants to take a very, very fine mesh and get something macroscopic out of that. Right? And infrared means that it starts with a mesh of a certain size and he wants to go larger scale.
Yeah, so it's related. It's just you ask different questions. And actually, the tool that people use in physics to understand this kind of things is this renormalization group. So What is the renormalization group? The idea here is very simple. If you arrange things like I said here with all these lattices of size a power of L, where L is, say, 2 or 3, a fixed number, what Wilson tells you is that in order to understand how the joint distribution of the little guys influences the joint distributions of the macroscopic averages, don't try to do it in one step. Do it by iterating a transformation. So if this is, if the mesh here is L to the R with R very negative, then you can look at the next lattice where the mesh is L to the R plus 1, okay, all the way up to L to the 0. Okay, and the idea is, okay, for each of these guys, look at the small guys inside, take the average, look at the joint distribution of these averages. It's completely determined by the previous one, and it completely determines the next one, and so they keep going. And there is actually a nice reformulation of this where actually everything happens on the same lattice, which is, you can say, unit lattice. Why? Simple, because these are random variables. The positions here are just labels, tells you which is which. And there is a bijection between all these lattices. So you can always pretend that you're actually on the unit lattice and keep repeating. So if you do the map, which takes you from one step to the next, this is the renormalization group map. That's the RG. And it's a dynamical system. Okay, so that's the really powerful idea of Wilson, is that studying this dynamical system tells you a lot about how you construct the measure, how the correlation decays. So, so dynamical system, you immediately think, oh, what are the fixed points, stable manifold, unstable manifolds, everything that you know from dynamical system, you try to exploit it here, and it's pertinent. Okay. So that's the RG. Now, in practice, how do you get a hold on the measure? Oops. How do you get a hold on the measure? Well, so we are interested in a measure on S prime of this space X. So suppose that you know what the space of test functions is. Then you get the space of the dual, the topological dual, which is S prime, the space of distributions. How do you get the measure on this guy? Say d mu. Well, there is two natural ways. One is to construct the characteristic function, which is integral exponential I phi of f d mu phi. Okay, so the characteristic function.
You want to find the measure.
Yeah, I really want to find the measure. So that's one way to proceed, construct that. And you do it by showing that for each choice of test function, you have these measures which depend on your cutoffs and all that. You want to show that it converges towards something, which is the characteristic function of a measure. So yeah, there are some things that you need to check. The other, before I mentioned that, so the other natural approach, which actually is, well, actually both are important in physics, but the other one is to construct the so-called correlation functions. So the moments of the measure. If you construct all these guys for any n and for any choice of test functions, you're happy also. Why are you happy? Because you have theorems which tell you there exists a measure and it's unique. So in this case, it's the so-called Bachner-Min loss theorem. And here, well, this is the Hamburger moment problem. And actually, you can write, I mean, the difficulty of, I mean, this is a famous problem in analysis. It's difficult because people look at what is the necessary and sufficient condition for the existence of a measure and for the uniqueness. That's very hard. What we want is just a practical criterion which tells us a measure exists and it's unique. And one possible choice is a growth of these guys as n factorial.
Why is it a one-dimensional problem?
Huh?
Why is it a one-dimensional eventually?
It's not a one-dimensional. Why?
But why, so it's not a one-dimensional, but it reduces to a one-dimensional.
No, I mean, you have, yeah, it reduces to the hamburger problem in Rn. I mean, in R, you need to know the solution of the hamburger problem on R of any dimension, the finite dimensional version, and then you use it here.
So
Here it's...
The path from finite dimension to infinite is standard, and what is difficult is...
Not really. I mean, we had to redo it, actually. I mean, but it's, I guess it's not.
It doesn't reduce to Kahneman's, it's really...
Well, Kahneman doesn't give us anything here, because Kahneman would be saying, so this is like saying the moment of order n is like 1 over n factorial. Kahneman is like 1 over m2n to the something like that. Has to diverge. Don't remember exactly, but in this case, it doesn't do any better than n factorial. I mean, it gives us something which is useless to check anyway. I mean, at the end of the game, you try to prove, OK, I have my moments converge, and they're bounded by a power of n factorial. Anything more complicated than that is useless. And if you allow just powers of n factorial, the power you need to take with Kahneman criterion is n factorial. So there's no point in... because this reduces to basically problems of extension of symmetric operators. So you use Nelson's analytic vector, or you use a Nussbaum, whatever. Here we just need the n factorial. Actually, in the in this case, if you look at the moment, typically what you get is a growth like square root of n factorial, not n factorial. So you have plenty of room.
In the latter condition, the test function are a product of n test functions. It's not just one test function of n variables.
In the what case?
In this second condition.
Yeah. So this is so you want to know these guys for any n and for any f1, fn test functions.
Yes, but it's always...
Where x is rd or qpd or...
No, I was wondering if the condition sometimes is like that you have one test function that is... So in that case, you are supposing a test function factorizes in n test function. It's always like this, the condition.
I don't understand the question.
Well, it could be one function of n variables rather than the product of n functions. And actually, when it's massless, maybe
you mean you want
f in the test.
It's just multilinear algebra. You mean you want a n-linear function of the field? You can do that too. No, because this actually, by the nuclear theorem, is the same. I mean, this is an n-linear symmetric. It's the same as a distribution, a single distribution on r or x to the n.
But you don't want a...
But that's the nuclear theorem. Huh?
When two variables coincide, no.
To get the measure, you need the... You don't impose. So it looks a bit similar, but it's not the same as doing Osterwalder-Schroeder reconstruction. And actually, you know, the interesting thing is that Osterwalder-Schroeder, you can allow more than n factorial. And you need that to construct the composite fields as fields.
Yes. But also you need one test function that depends on n variables. Because you have to avoid, because at coinciding point you want to have zero. This test function must be zero. So if the variable in f1 and the variable in f2 are equal, you want to have a zero in the test function because otherwise
well, you want to avoid the diagonal if you're doing, but I mean here you can't. I mean you need to eat up the diagonal. I mean you need to to work on the diagonal too. So so for instance, your starting point, you want to start from a Gaussian measure, and then you perturb. So you start with the massless. You can construct. You just set this equal to the usual thing, 1/2 f, the covariance f with your massless 1 over p squared. This gives you a continuous. This gives you a continuous bilinear form here, and so you can apply the Bachner-Minlos to construct the Gaussian measure that you start from. So that's the easiest, cheapest way of constructing the starting point. But you can only do that, as you know, in dimension 3 and above because of the 1/p squared singularity. Well, actually, this is an infrared problem, so it's not really. I mean, the test function decays at infinity, so you don't really have a problem controlling what happens the diagonal.
So the ultraviolet Schroeder thing you can't use here because you don't have OS positivity for that.
I don't really care that. My point is, I don't care about Osterwalder-Schroeder. I'm not trying to construct quantum fields in Minkowski, especially since I'm going to talk about QP. It has no meaning, really. I mean, you can try, but
the moment problem, you see a composite field, maybe then you would not have n-factorial growth.
I mean, if you have composite fields, you're probably going to have worse than more than n factorial. So, just by Wick's theorem. Yeah. Okay. Okay, yeah, so, all right. Okay, so this is how you try to get a hold of the measure. But in both cases, what you're doing is looking at averages of observables. You're looking at things like this. F V lambda. So the integral is over this S prime minus V lambda phi, V mu C of phi. Okay, so this is your Gaussian measure. So which corresponds to just this quadratic form here. And this is your perturbation with the phi 4 and phi square integrated over some box lambda. And f can be either exponential phi of f or a product, for instance. But in both cases, that's what you want to handle. And so you want to take here measures depending on parameters, and you want to control this when you take the limit.
You like this thing, do you think right now that you're on a lattice or not on a lattice, or what?
I'm going to make things more precise. I'm just giving the general ideas for. All right. So here I want to take two limits, and in this order of something like this. So what is S? So my big box, I'm going to take the big box here to be of size L to the S, where S is going to go to plus infinity. And the little boxes, the small lattice, again, has lattice mesh L to the R, and R goes to minus infinity. And I need to take the limits in this particular order. First, infinite volume, and then lattice go to 0. For a given observable, for instance, exponential phi with a test function.
The other way around, too, right? You could do it the other way around.
Yeah, you can, of course, but the more canonical is this. I mean, okay. So that means you need to specify the reference measure. So that means that you have to go from a covariance. So a homogeneous distribution, Laplacian to some power, where you have all the scales, to a version where you have regularized. So you killed momenta which are of size more than L to the minus R, which becomes very big. Okay, so you need to introduce a modification. With this modification, your Gaussian measure will be typically on nice, supported on nice function, not just distributions. And here, the V that you want to take is just this thing. So I'm going to call mu the coefficient of phi squared. And people do this thing. I'm going to explain what it is. So CR is a regularized covariance. And here another parameter GR, phi 4 of x dx. Sorry. And what these things are is so-called Vic ordering with respect to that covariance is just Hermite polynomials. So this guy is phi of x squared minus CR at 0. So the the kernel of that distribution at 0. And this one has a more complicated formula with phi 4 minus 6 C of 0 phi squared plus 3 C of 0 squared. These come from Hermite polynomials. Okay, and so you want to to adjust the GR and the mu R so that your limit exists. So the couplings,
how is R related to S? I mean, R has just come out of the
S. So R is the size of the little boxes.
yes.
S is the size of your big volume lambda. So the big volume. So everything is, you need to put a big volume. So the integration here, you can write it like this if you want. The integration is over a volume determined by S. You have two.
Okay, but that's an R. I didn't understand your writing there. That's an R goes to minus infinity.
So the little thing is L to the R.
Okay.
And the big box is L to the S.
Okay.
S goes to plus infinity, R goes to minus infinity.
So you're showing us how the V has to move with the R's, right?
Yeah, so the precise statement is to find the correct mu and R such that if you plug here something like that, this limit exists and gives you a measure that has the properties that you want.
You're talking about right now R is fixed and S goes to so this integral is an integral or a sum. What do you mean by the integral of lambda S? Lambda S you think of
Lambda S is a box, so you integrate x dx
really
over that box.
So that's why I like to fix the S first and then let the R go to infinity, because effectively that's what you're doing there, right?
Fix the S first.
Because you fix the S, you're giving the R dependent.
Yeah, but I mean, I think the more canonical way is to take the infinite volume limit. But I know that people usually, for 542, for instance, you put the unit box, you construct the theory. Yeah, yeah. I won't do it the other way because I want to use the RG.
R is fixed and lambda S, so it's kind of discrete sum. You really mean a discrete sum? Or,
It could be. So, for instance, if you use a lattice regularization, but that's not the only way of.
That's what you explained here. So that really
So I didn't tell you how you define the C. Okay, so if you're on R, I want to talk about QP. That's why I didn't want to. Okay, so if you're, this is dk 3, 1 over k at the power, so e to the I kx. Here you put the power 3 plus epsilon over 2. That's your massless free field with this funny power of the Laplacian. So that's not what you want to use as a starting point. You want to use CR, which is, it's not exactly how I put the cutoff, but it's kind of the same thing, but you you put condition that k is not bigger than L to the L to the minus R, which is going to get very big. You just put a cutoff on the.
Yeah.
So that's your CR.
To match with your picture, that cutoff has to do with that's really a Riemann sum. If you're going to match, but you're just.
If you do, yeah, you can
go back.
really work with the lattice. In this case, you're right. This is a Riemann sum, and your field on the lattice is constant on each little cell, but that's not the only way to do it. Okay. Actually, the nice thing is that on the p-Adics, it is constant. Without doing anything, it's as if it's on a lattice. Okay. All right. So So how to proceed? Well, so first since you want to use the RG and you want to work always on the same lattice, there is a first step, which is a trivial rescaling. So, and that's basically doing the following. So since you want to work only on the lattice L0, and initially you had this lattice L sub r, what you do is you replace your field here. You write it this way. You write it phi x is L to the minus r something which is called the dimension of the field. And I guess I should use a different letter, maybe psi of x divided by L to the r, and I'm putting between quotes. What you want, so so r is negative, you want this to be much bigger by, and this thing here, you can think of it as a field living on the lattice L0. So if you pick for this number here, 3 minus epsilon over 4.
Corresponding to that power you have.
Mm-hmm. Exactly. Or, I mean, this particular choice of what the covariance is, if you pick precisely this relation when you go from a field in the small lattice to big lattice, then the nice thing is that if your original guy is sampled according to this regularized covariance, it's the same as taking this thing cooked up with a psi, which is sampled according to C0. Okay, where you put the cutoff at scale 1. And if you think in terms of, like you said, discrete things, that means that your psi is constant over the unit blocks. So it's really, you can think of it as a lattice field on a unit lattice. Okay. So when you do this, then the RG, what is the RG? Applied to observables like that, it's the following. Okay, I gave the intuitive idea, but it's not just an intuitive idea, it's an identity. And the identity is the following. Okay, always. So what you do is you write your original covariance C of x as, so this one basically tells you that the covariant, the momenta, if you want, are of size at most 1. Here you're going to take momenta of size between 1 and L inverse, and whatever else is left, that's a new covariance, but this new covariance is actually a rescaled version of the first one. So precisely it is 2 phi C0 of x over L between quotes. Between quotes because this is kind of annoying. Over R, you take x over L. Over QP, you take L times x. That's how it is. Yeah, this is very, I'm working in the space X, which could be R or QP. Everything I'm saying is, so far, is true for both. Okay, so from this decomposition, you have your original field psi. I'm not going to call it psi. I'm going to call it phi again. I'm sorry. Your original field phi is equivalent to a sum of 2 independent fields. So it has the same probability distribution as taking this thing, phi L plus zeta. That zeta is sampled according to the Gaussian measure with covariance gamma, the so-called fluctuation Gaussian measure. And this is of the form L minus dimension of the field, phi of x over L between quotes, where this guy again is sampled with the same measure C0. There is this built-in self-similarity. So using this, you can start from the formula above over there. And, oops. Okay. You can start from the same formula here, and actually it's going to be written exactly the same with a new. So what you do is you write phi here as a sum of two things like that, so you transform this into a double integral. And what you get here is that this is equal to something which looks the same, v prime lambda prime phi d mu c0 phi. So this is starting from unit covariance over E minus V prime lambda prime phi d mu C0 phi, where what are these guys? So E minus V prime lambda prime of phi, this is integral of V lambda of phi L plus zeta, d mu zeta sampled according to this fluctuation covariance. And the new f prime here, oops, is given by a ratio. So f of phi L plus zeta e to the minus v lambda phi L plus zeta d mu gamma zeta over the same thing without the f. Okay, it's just playing with double integrals, recombining things. It's an identity.
Just integrating out the fluctuation variables, right?
Sorry?
Just integrating out the fluctuation variables.
Exactly. But there is no, the nice thing is there is no, this is inequality. Okay, so it's written exactly the same way, but with different things. So you started with an observable, you get the new one. You're starting with a certain potential, depending on g and mu, you get the new guy. Actually, also the volume. You started with a certain volume lambda, and you get the new one. And actually, this one is shrunk by a factor of L. OK. The important thing is that the flow of the potential is not dependent on the flow of the observable. So what we did so far, I mean, I said in the abstract, what we did is what I'm explaining is a progress report. What we have is a very good control over this. And we still have to do more work to control the full RG, which is the flow of all the observables.
On the p-Adic, you're saying?
On the p-Adics. But I think if we get a good hold over this, we can answer all the questions that I mentioned before, even constructing composite fields, operator product expansion, and all that. But OK, that's that's for later. But this we understand very well. So the
You don't understand that very well in the continuum, but you're saying on the p-Adics you understand it very well, right?
No, I mean, we understand it as well as over R. I mean, for this part, yeah.
Well, that's in general, that's quite a...
No, I'm not saying in general. I'm saying on this particular model.
Well, he's just saying for one step or something.
Oh, for one step, well, yeah.
No, I mean,
the point is that V prime is right now local now. It started out being
yeah.
local, but it's no longer
Over the p-Adics, it is local, so it's the usual RG. So it's much easier. But so far, what we actually proved. I mean, Brydges-Mitter-Scoppola and also myself did already over R. So we did that plus a little more. I'll explain on the picture what we. I have what, 5 minutes, 10 minutes. I'm gonna go see. For the Atia talk.
Yeah. So let's say 5 minutes, and then we can take a little break and then come back and else wants to.
All right. So now here is the picture. So it's a dynamical system. And I'm only studying the V to V dynamical system.
And you're pretending it's local or not?
On the p-Adics, it's local. So I guess I didn't have time to talk p-Adics at all. It's completely local.
That's the advantage of the p-Adics.
Yeah, actually, I spoke about both R and the p-Adics so far because everything there is so p-Adics is a funny field with its own distance. In R, you know, these lattices that you introduce, it's artificial. They don't come with Rn. You have to decompose into boxes. In p-Adics, it's there. It's the structure.
Decomposition is natural.
Yeah, it's completely natural. Basically, over the p-Adics, there is a subring called ZP, which is the p-Adic integers. So we're looking at QP3, and if you take the quotient by the p-Adic integers, this is your lattice L0. It's given by the space itself. Everything is much more natural as far as RG goes. For instance, this lumping together random variables, taking the average, I mean, it's just imposed by the geometry. So that's why the RG is much simpler. It's local, and it's the familiar hierarchical renormalization group. It's not an approximation. It's the RG that you need to do. Okay.
So if V is a function, so V will, yeah. So your V will be another V. It will be really another V prime, right? It will be another.
Yeah. So what I'm going to draw roughly is the space of V's. So the V's, you need 3 coordinates to get a hold of them. Basically, what you do is you write e to the minus V lambda of phi as a product over boxes in your lattice L0 of what? Of exponential minus GR integral phi 4. And this is over the box delta. And mu r, no, sorry. I mean G mu integral of phi squared with the Vic ordering. And then outside the exponential, you introduce another function of phi restricted to the box delta. That's how we want to look at the evolution of the V's. So starting from a V which looks like this, you get the new V which looks like this, but with different G's and different K. Over the p-Adics, so not only things are local, but using the same decomposition in the way of introducing cutoffs, which I didn't talk about, that uses some Fourier analysis over the p-Adics, but the field phi sampled according to the Gaussian measure with covariance C0 is constant on the blocks of size. So on the blocks of size 1, phi sampled with C0 is constant. And even more than that, if you look at a box of size L, and you look at the fluctuation field zeta sampled according to the covariance gamma, then if you look at 2 different boxes of size L, zeta here and zeta here is completely independent. So that's why the RG is local. It's completely independent. So it's very simple. So in other words, the function here, k, actually forget it's a function of one variable. Okay, so k is actually a function in C9 of R to R. We need some derivatives to control, but
you will have that in the hierarchy.
And actually, we extract a little bit of the k, so it's something actually I code R. So k is actually R plus something explicit. I don't worry about it, but the RG, as long as I'm just looking at V to V, not the F's, there is a direction called R.
What does k have that makes it distinguishes it from what you have on the exponent?
Huh?
What property does k have which distinguishes it from the exponential stuff you've written?
Well, at the beginning, you don't have any k. So you have just this, and the product is what is the exponential integral over the volume.
Right.
But then when you iterate RG, you get nasty stuff. So you need to keep track of them, and you put them here.
Okay.
That's.
But usually you have the first so many derivatives are 0, right?
Yeah. So you wanna. So there are some guys which you can't leave here. You have to put back up, and so. Okay. Uses the non-uniqueness of this representation. So the k itself is something explicit. I won't write, depending on G only, plus R. So the space we're working in looks like this. There's a G, so this is just one-dimensional, infinite dimensional, but under control with a in some Banach space with some norms. And how does the RG look like? Well, so this is the so-called UV fixed point. It's at 0. That's what we want to get away from. There is a fixed point here in the infrared, which is roughly at distance epsilon. So everything actually is happening very, very close to the Gaussian. That's why we can do analysis. If we could do epsilon equal 1, then we could do Ising in 3D, but that's too hard. So actually everything is very close, but I'll blow up the picture a bit. So this is expanding direction with eigenvalue 3 plus epsilon over 2. So it's very, that's the mass direction, it's very expanding. And then the direction of the 5-4 coupling, it's also expanding, but with a much weaker rate, which is L to the epsilon. Okay. And this direction is contracting. So you cook up how do you define your new K so that everything which is non-contracting, you put it upstairs in the G's and the mu, and you leave what contracts. So it's meant for that. And so here, what's expected is that there is an unstable manifold here of dimension 2. This guy has a stable manifold of codimension 1. And so there is an intersection, which is a curve going from here to here. So what we did, I did it over R, but now we did it over QP, is to construct a whole bunch of trajectories, discrete trajectories, which go from here to here. So that's done. We did even more. We did the solution. I mean, at least we still have to really handle this to be able to claim that for sure. Constructing a sequence of starting points that corresponds to the choice of mu r gr. What do you take? These points typically are not in the so-called bare surface. So they have some stuff here. You want to start from clean starting points without a K. So just this, and construct your measure that way. So that means that you need to take, so to make things simple, you can assume that the bare surface is r equals 0. But it's not exactly it, but okay, so you have a bare surface like this, but the curve here has no reason to stay in that plane, right? It can move a little bit. So what you want is to find a sequence of starting points. This corresponds to your GR if you want. So GR mu r is the same as, I'm going to write it PR, a sequence of starting points. You can start with P0, P minus 1, P minus 2, and they're actually going to go here, such that you want, so the criteria, I mean, you really want to follow the flow of the Fs. We can't do that yet. But common wisdom says that what you want to have a well-defined measure in the end is that if you iterate the proper amount of Rg so that you get to unit scale, you want your effective, what is called the effective theory, so the point to stabilize. So what you want is that if you iterate this guy once, poof, this guy twice, poof, this guy 3 times, you want these vertical things to stabilize somewhere. Okay? And the field theory that you construct in the continuum has to do with these stabilizations. You can think of a quantum field theory as actually a 2-sided trajectory. So morally, so we did that. We show that you can take starting points on the bare surface which converge, blah, blah, blah. And so morally, that means constructing a measure which is massless and everything. Okay, but to remove the morally, we would have to study the F. So we still have to do that. But I think we can do it. OK.
Well, thanks
sorry, no mention of p-Adics really.
We're rushing with the end, but I think people.
Okay.
But I think what I propose we do is, I'm not going to go to repeat the talk, but many people will probably want to go. I don't know whether you want to go.
I don't know.
Well, we can meet afterwards again to talk about other things if you like.
You said geometry of the universe?
The universe, yes.
Yeah, maybe not. Yeah, I guess.
Okay, so what I'm going to do, what I propose we do, you and I do it, and anybody else who wants to join us, is to get some tea, come back, and then talk some more about some other things that you've been working on.
Okay.
Great.
So I just switch off,
Yes.
Brian?